Hey guys, Mr. Gagnon again. We're going to look at, in the homework, we're going to look at number 22 now. Okay, we're getting into some of this dynamics of uniform circular motion where we're given a mass. So again, looking at objects that are swung around in a circle. Okay, we're given a mass of 6.8 kilograms. Okay, now guys, as you're going along these, watching these videos, okay, you're going to try to realize in 6.8 kilograms now, keep in mind that you're going to see that the weight of that on Earth in pounds, okay, is about 15 or so pounds. So consider this: when you're swinging this thing around, you're swinging a 15-pound weight, if you will, around in a circle. So that'll give you an idea of what kind of force you need to pull inward. Okay, so we've got a force, net force of 135 newtons. The velocity is 45 meters per second. So velocity is coming out here. The force is pulling in this way. We know there's an acceleration this way as well. So we've got a few things to consider. Okay, first thing we have to consider is what they're actually asking us, and they're looking for the radius of the motion. So we're looking for like the size of this string. So that's the question mark. Okay, so we're not going to directly get there because we're given a mass, we're given a force, we're given a velocity, and asking for a radius. So we're not going to get that radius directly, but we got to look at the two formulas that give us a radius in it. The first formula is the acceleration is v squared over r. Here's a radius. The second formula we look at is the velocity is 2 pi radius times the frequency. So let's see which one of these might work out for us to get the radius. So I'm looking at the first equation and I'm saying, well, okay, I've got a velocity. I do not have an acceleration. Okay, well, we're not going to be able to use this one quite yet. Now, if I look at the second formula, okay, I've got a velocity. Ooh, I don't have a frequency yet. Okay, so now if you look over here, the frequency or the period of motion is not even discussed in this problem. So I'm going to call that formula, we're going to trash that one. Okay, put that one in the trash can. Okay, that goes in the dump. Okay. The formula I'm going to look at is the A is v squared over r, because we know that the net force, according to Newton's second law, is equal to the mass times the acceleration. Or in this case, it'll be centripetal acceleration. So we know net force. Okay, we got it. We got a mass. We should be able to get that acceleration. No problem. So if we just solve, excuse me, for A, divide through by m. So A is going to be the net force over the mass. We've got a net force of 135 newtons. We've got a mass of 6.8 kilograms, and we should be able to get the acceleration from that. And yes, I ended up with about 20 meters per second squared. We're going to just say it's 19.9 meters per second squared for the acceleration. 19.9 meters per second squared. Now again, we still haven't found for the radius yet, but now I've got the acceleration. So I've got the acceleration, I've got the velocity, and now I'm looking for the radius. So if I bring that on down here, okay, and I'm just going to plug in what I've got here. Okay, so we know A is v squared over r. Now guys, if you want to, you can rearrange the equation prior to solving, or you can plug in the numbers and solve once the numbers are in. I switch back and forth between both ways, so that in this case, we'll just leave the formula the way it is. So I've got an acceleration of 19.9 v squared. So we're looking at 45 meters per second. You're going to square that over the radius. So what I'll do is I'll multiply both sides by radius. Okay, and I end up with 19.9. I'll leave the unit out here for sake of space. 19.9 R equals 45 squared. Okay, so in dividing through, 45 squared over 19.9. Okay, R is going to end up being whatever this value is. And after solving for 45 squared over 19.9, I end up with a radius of 101.8 meters. So that radius right there, that distance there is 101.8 meters. And I hope that helps with a little bit of the dynamics.